So we will start with the geometry modeling. So as you have the mental picture of geometry with you, you can just go back and check out the slide. We'll start drawing the region. So here let's go to the region, and as you can see, we'll go with the domain region of polygonal shape. So we'll start with a point from at a point which is 15, 15. So let's make it 15, 15. Yeah, here. So let's start with this point and go to the left direction and start creating it. You will see why we are doing this from 15, 15. We go down to the origin and then move left towards the point where we meet a 70, 0 point, and we go up to the 30-meter height. As you can see, the length is 30, and we'll go ahead and we'll move to a length of 20 meter. Yeah, 20 meter length is covered, and now we'll join this point. So otherwise, if we don't have started with the first point at 15, 15, we'll be having a split region type of problem. So we have here with us the geometry of the shape which we want to analyze. We'll just close this. So this is the geometry. There are other ways to do this, so I will directly show you that. It will also give you a quick tutorial on the interface of how to do it. I'll just Control Z or undo this whole process. Now we'll again draw the geometry. So if you are starting from this origin, you have to go to the length of 70, then you can go up to the length of 30, then you have to go up to a length of 20. Yeah, here 20. And then what you can do is that you can directly you don't know where to, which points to at which point to be. It will be 15, 15, but if you don't know, what you can do is directly you can drop down to a length of about 15 meter, and then you can directly jump to the vertical axis and join this point. So we have one section. Now we can create another section from this point or 15, 15 point, and directly join here and create one more triangle. So we have two regions now, and what we can do is with these two regions, what we can do is that we can merge them. So we can go to merge region and then select this region, and we have merged these two regions. So there are several ways to create a geometry, and it's quite simple, but anyway we have to look into them. So after geometry, what we will do is that we'll go to define materials. So we'll first define the materials. So there is no material initially in the list, so we'll add a material. It's a new material. You can call it MC soil. So that's what I'm going to call it. And now we'll see what various types of material can be defined here. We have more columns, spatial more columns. So I will teach you one by one what all these type of material are based on. So basic more column material will require the cohesion and phi or internal angle of friction and unit weight. So it's the basic more column, and it is much simpler, most simple to define this type of material. There are special more column type of materials which basically uses spatial functions to define cohesion and internal angle of friction with either you can define them based on the value of x and y. Basically, if you go with the linear function, you can create a function, and in this function you can just add cohesion versus x or cohesion versus y, and there are several type of spline data or linear data which you can add. So with the depth, so basically it's not a spatial more column, but it's kind of a slightly anisotropic material where c and phi are changing, but we are using the envelope of more column to define the plastic properties. So special more column basically allows you to create c and phi, which varies with the material geometry or x and y. Now there are this high strength material which we generally use which doesn't has any c and phi value. So if you are having a let's say steel or iron kind of geosynthetic, we can use high strength material, but that's not the case generally. In a geogrid or a geosynthetics, metallic geosynthetics, we use geosynthetics but still apply the pull out and tension properties. But high strength materials can be termed as very high rigid rocks, very rigid rocks, or a metallic component of any reinforcement. So these are high strength. So after high strength, we'll see that we have a bedrock type of material. Bedrock material is basically impenetrable, so you don't have to define mu, C and phi, any kind of failure mechanism, because it will not fail basically. So there is no need to explaining it further. Undrained material is basically a cohesive material, which is a saturated kind of, you can say it's saturated clay, or basically any kind of cohesive material where you can only provide a cohesive total cohesion, because this in generally we say that in clays the draining process is very slow, so you can use this kind of material where we have very shallow water table and we have clay. So undrained material can be used in that case. Now compound strength. So basically if we have different types of failure envelope like Moore column and so on, like Hugh-Brown, shear normal function and so on, we can compound them in directions and add them into this parameter. So we can just add this material which we have none right now. So if we have materials with us, we define 3 types of soil. At each orientation, what type of material behavior can be present, can be there in that kind of material, can be presented by this kind of compound strength. So it's very complex type of material, but if you have that kind of occurrence in field, then you have to go with this kind of parameters. But I'll let you know that 90% of the time you will use Moore column for the soil material, and you will use Hugh-Brown parameters, which can also be simplified into Moore column. If you have seen any software like rock data, and there are curves which can directly simplify Moore column parameters from Hugh-Brown parameters, and vice versa. So you will be using mostly 90%, or let me call you 99% of the time, Moore column plus Hugh-Brown. These two failure mechanism or plastic parameters will be good enough to know. So after compound strength, we'll see shear strength with depth. So we can define cohesion and rate of change of cohesion with depth. This C basically is the shear strength, not exactly cohesion, but you can go ahead with it. So if you know the in general we say this actual strength, or in this case we can call it cohesion. You can define a rate of change at which this cohesion will be changing with the basic depth. If we are going down, we generally see that with depth materials become stiffer and stiffer. So in general sense, you can just define a rate of change of cohesion and initial and final cohesion values. So with depth and datum, you can also do the same thing. Datum basically means that the geodetic coordinate systems, but you can, in geotechnical engineering, you can basically use the depth parameter. Anisotropic strength will, in which we will have a different cohesion and different angle of friction in vertical and horizontal direction. It basically depends on what type of loads which we are getting on a soil. In gravity loading, shear failure is most prominent. So we generally use this cohesion and friction value, which are working in both direction, which are same. So in any case where you have different strength along horizontal and vertical direction, you go with this anisotropic strength, and that generally happens when you have foliations and that kind of geological phenomena in the field. Shear and normal function, in which if you have performed a triaxial or direct shear test on the material, you can directly go with shear and normal function. So you can create a function and add the value of shear and normal spline data. So we will be looking into it in one of the example problem, so as to cover the whole spectrum of material definition. So you can just create normal and shear parameters, which you can get through triaxial or direct shear data. So you can input the values and it will create a spline. and it will dictate the properties based on that function. Now Hooke-Brown is just simple Hooke-Brown parameter. You can get it from the GSI values, RMR values, and Q values. This parameter UCS is the rock strength basically, and MB, S, and A are the Hooke-Brown failure envelope parameter. You can also calculate it based on MI and GSI value. GSI value, which we have seen, can be calculated based on the RMR and Q values, and this disturbance factor and MI values. This can be calculated based on what type of rock strength we have. So either that or this, you can basically calculate the Hooke-Brown parameters based on the lectures which we have seen earlier. An isotropic function, again it's quite similar to the anisotropic strength, in which we can create a function. So you can see that geoslopes basically covers all type of material which can be used in field in a long spectrum. So I will not go very deeper into this, but these functions can be created based on any linear mechanism. Either you can create a spline or you can create a add-in function based on what you want to have. Like there are several add-in functions, but you can create your own function. I guess just by adding points into the spline, like you can go with whisker function, and there are models, but you generally don't use this because these are very complex parameters. You can create various layers, which we will also see in our next example problems. So an isotropic function basically dictates the anisotropic nature of your basic anisotropic nature of your soil. So again, combined shear strength variability with depth can be also calculated for the phi, and as earlier we have seen that the shear strength parameter with depth only uses the cohesion value previously, but here we have the phi value which is the internal angle of friction, which can also vary with the rate of depth or whatever depth we have. So we can have just we can have initial layer of initial value of the cohesion, and we can just define the rate of change, and based on this ratio of C by Cu ratios, you can calculate whatever phi and C we have been getting for that depth. Again, datum, it will do the same, but it will be with the datum. So Shansep is a different type of failure mechanism. So here you have to just use C5 type of reduction mechanism. So I will not go a lot deeper into this parameter because it is rarely used, but in some special cases this can be used. But the other prominent one is the bilinear, where you can just define this phi 1 and phi 2, which are the inclination of tau and sigma. Basically, if you have a tau and sigma curve of your soil, then if you have bilinear curve, basically there are one line initially going from near origin, and then again it turns. You can have both the angles defined for that, and at the point where it shifts, you can create the normal stress value of that point and the cohesion value of the bottom line, the first line, because the second cohesion can be automatically calculated. So these are the bilinear. However, for this problem which we are going to attempt right now, we will use more column parameters. So you will see that we will be using more column parameters, and we know the parameters from the lecture slides, that the unit weight will be 20, the cohesion will be 20, and the phi internal angle of friction will be 20. So it will be a 20 20 20 example function, example material. So we have defined this. You can also change the color, play with it a little bit, go with pink if you want, go with anything. So there are a lot of things which you can do. So I'm just going with some specific color, and I'm just going to close it. Other properties of the material, like suction, R envelope, liquefaction, you should generally go with the default values if you don't know anything. Otherwise, if you have performed experiments, permeability experiments, and capillary experiments on the soil, you can have these values. Otherwise you can just go with the default values. Now if you have the R envelope values based on stage analysis, you can go with it. Otherwise you can just go with the default. Again, for the liquefaction, everything I should have suggested will go with the defaults. Now I will just close the material parameters. So everything else section R envelope are experimental based. If you have performed any experiments like cyclic ratio, CRR, and CSS, cyclic stress ratio and cyclic resistance ratio, you can come up with this CSS and collapse angle values. Otherwise you can just go with the default. Again, for the R envelope you have to perform UU and consolidated all type of triaxial test to come up with this type of material. But in general you can go with the C and 5 parameters. I'm just going to close it now. So we have defined our material and we have seen what different types of material can be defined in GeoStudio slope W. Now what we will do here is that after defining the material, we will draw the material. So we have the material with us. Now we'll just have to click on the internal part of the area. So we'll just click here like this, and we can see that our material has been assigned to the whole area, and we'll just click on cancel. So after assigning the material, what we have to do is that we have to define several type of seismic loads, RU values of pore water pressure parameters. So we'll just go to the define project setting and we'll see what else is left. So we have to define the PWP conditions in the RU, and in the slip surface we have to use the entry and exit method from left to right. So you can see that in this method your slip surface will go from right to left. So we'll have to change that as well. So your slip surface will be going from right to left, as you can see the screen here. So anyway, we'll first start with the RU parameters, which are pore water pressure parameters. So I will just define a RU coefficient of 0.25. So 0.25, this is a dummy coefficient which you can guess based on your own experimental understanding. However, this RU of 0.25 generally represent how much saturation has been achieved, and 0.25 saturation like almost a half of the height of saturation is very much. So 0.25 is considered to be very good value, a very conservative value of RU. So after that we can go and we can define the seismic coefficients in, I'm guessing seismic loads, sorry for that, for a bit confusion. So in seismic loads we will define the horizontal and vertical earth pressure coefficient, which you can basically refer to. So you can refer to IS 1893 part 1 for these values. However, you can take dummy values of 0.15 of for horizontal earth pressure, horizontal seismic coefficient, and vertical 0.1. That will be good enough for your understanding right now. But you can just go on and check out Indian Standard 1893 or other parts where you can just calculate these values based on the zonal provision which are provided in Indian standards. So these are that seismic and earth pressure coefficients has been defined, seismic and pore water pressure coefficients has been defined. Now we'll go to the project setting, and because we can see that our geometry will require us to calculate the slip surface from right to left. So we'll go and change the direction from for slip surface from right to left, and we'll go with the entry and exit method. So we'll just change the setting and just cancel this. Now what we'll do is that for the analysis to run, we have to define the entry and exit points of the slip surface. So we'll go with the first we need to define the right side of the entry because from here the slip surface will enter. So we want to make our slip surface anything from 0.4 to 0.3. If you can zoom in, these are 0.4 and 0.3. So and these are 0.6 and 0.7. So this will be the exit points line segment where our slip surface will exit. So that's what I am going to do. So you can just hover over it, and 0.4 the coordinates are 50, 30. So the right point I guess is the 0.3. So for 0.3 we'll use the 70, 30. So we'll just type in 70. and you go down and you will see that it's 30, because it will automatically catch the geometry. For point 4 it is 50,30, so left point will be 50, and you'll just click on bottom point and it will see 30. So number of increments will be 8 by default, but I generally go with 10, so be a round figure side, be on the round figure side. Now for the point 6 and 7, we have to define the right point. Now right point is the point 7, so we'll define it based on the hover coordinates after hovering, which are come out to be 15,15. So we'll just click on 15. So you go down and you see 15, and the left point is 0.6, which is 0,15. So you'll just click on 0 and you go down and you get 15. Now again the number of increment over the range, I will go with the 10. So in both the lengths we'll have 10 increments, and number of radius increments can be also included as 10. So you can go with 10 by 10 by 10, 1000 slip surfaces can be analyzed for this kind of analysis. So let's just click on close, and we can see we have defined the parameters for entry and exit slip surface parameter. So what this parameters will suggest is that your slip surface will entry from this side and it will exit between 6 and 7, entry between 4 and 3, and exit between 7 and 6, and there are tens of combinations of each points, entry and exit, and the radius. So we'll see how this analysis will go on. One more thing which you can do is that you can fine tune this analysis. You can also fine tune the overall analysis setting by going into advanced and the minimum depth of slip surface and so on. These parameters can be controlled. However, in most of 4 tutorials we will not be looking into these parameters, because by going into this parameters with default setting it will be good enough. So there are a lot of things which you can vary based on this parameter, like minimum slip surface depth, number of slices which you can generally increase to suit your iteration methods. Number of iterations can also be increased, and solution method can be changed from root finder to linear search. So if you want to play mathematically with it, you can change a lot of things, but this is a basic tutorial, so I will not go into detail. So I'm just going to close it, and we see that our slip surface from right to left is defined and been created. So we'll just close this. Now what we need to do is that if there are any loads which are currently not here, which we'll be looking into later tutorials, so we'll just go with the gravity loading, which is by default the loading type in the GeoStudio. So we don't have to define the loading. What we can do directly is that we can just go here in the solve manager and start the analysis. So we can just click on start, but before that we'll just save this file, and we'll have a default folder here, and we'll just call it test file, and we'll just save this file. So this file is now saved. Now we'll just start the analysis, and you can wait for some time for this analysis to over, and it will be not a long time after this is over. So you can see, so let me just manage this so that it will be much visible to you. So you can see the factor of safety. There are several columns like number of slips surface, factor of safety, x center and y center, or the coordinate of center of the slip surface, the radius of the slip surface, and the detail, which is the critical, the lowest one. You can see here, based on that the lowest slip surface comes up with the factor of safety of 0.926, and you can see that the factor of safety keep on increasing as you keep going down, and you will see this red point is the actual center of the slip surface. So you can just sorry, not this one, but let me check it out. So these are the basic factor of safety, but not the radius. So if you want to see what is the actual center, you can just locate these coordinates. However, there are much better analysis types which can be adopted for this to locate the radius of this output can also be generated in form of like you can just get this output in the form of you can go to solve manager, or you can just go to slip surfaces, and you can maybe they are not opening now, but you can just see that you can get this all of them output in the form of a different type of output format. So what I meant to say is that you can get all these data in Excel sheet or something from the software as well. So you have to go to view, and you can just click on report, which will basically allow you to save this report in the form of HTML file, and you can just save this here, and it will open in your Google Chrome tab. So here you can see that there are different slip surfaces, and with those slip surfaces you will see what type of slices you have, and you will basically get the it will be for the whatever slip surface you get different forces, and for those file you can basically get what type of analysis has been done. So I'm not going deeper into that. I'll just go again into GeoSlope and save this analysis, and I guess you can play around with it a bit, and there are different type of slope stability mechanism which you can adopt, but for this specific tutorial I guess this is over, and we'll in the next part look into different type of problems.